Today I have to leave a little bit earlier, so we'll be up to 3:10, okay? And then, but Wednesday we will recover 20 minutes, so Wednesday will be a little bit longer, okay? So be prepared, huh? Coffee? Okay, so last time, it was Friday, we started with a very large introduction, so we have new, you were not here Friday.
Yeah, I was on
Yeah, what?
Vajia.
Vajia.
Yes.
Okay. You are mathematician, physics?
No, I'm from computer science.
Computer
Computer science.
Computer science, okay. Okay, so, yes, we started, you remember we defined these two adimensional numbers, which were epsilon and sigma. Then we also defined like the omega, small case omega, but the epsilon was the ratio between the time of rotation and the motion time scale, considered as a time as a time taken to a person to travel a length L in with velocity u. Okay, so this was 2 pi u over L omega, capital omega, and this was the kinetic energy over the potential. So it was capital P, okay? So which was 1/2 rho 0 u squared over delta rho g h. Okay, so everything was written as scales of motions. Okay, so it's important you remember the definition of scales of motion are like sort of quantities which measure the order of magnitude of the phenomena. Okay, velocity, length, height, and density. Okay, and also density variation. Okay, so we said that when epsilon is smaller order of 1, and when sigma is smaller or order than 1, we can take into account rotation and stratification effect in our dynamics. Okay, so this is very important. So these are the, let's say, hypotheses for GFD phenomena. Okay, so what we want to do now is to try to feel what is the limit of this approximation. So what happens if epsilon is order of 1 and sigma is order of 1? Okay? So this is the limit where we can define a length L, which when this is order than 1, we can for this moment avoid these two numerical quantities, 2 pi and 1/2, they are just numbers, so we are just not more interested in that. So if this is 1, L will be u over omega, right? And if sigma is order of 1, we can solve for u, and we have that u is order 1, the rho 0 gh over in square root. Okay? So from this, we can use this value of velocity time scale and specify this length scale. So this length scale is very important because it is very simple how we found this value. Because we just consider the minimum length that we can have and the maximum velocity that we can have. Okay? So, according to this, we found a length scale, which depends on the rotation rate of the planet, depends on the gravitational acceleration on the planet. So these are two numbers which are parameter fixed for the planet, and then correspond to the height scale, typical height scale, where a specific density variation is occurring with respect to a background density.
Please at least that's a recording.
Yeah, it's recording. Thank you very much. Yes, please. If you just help me to remember to resist. In any case, there are also the old lecture from the past year. So you can see how less hair I have. Okay, so let's take our planet, Earth. So from Earth, we know omega. You remember the number? 24 hours, but the number of the frequency of rotation is 7.29 10 to the minus 5 second to the minus 1. Okay, so it's not important. This is something that I want to tell you as a friendly advice. So obviously numbers are numbers, but it's very important that you remember by heart your some specific number. Okay, so this one, for example, is very important because it's something that can be asked you to the at the exam. So of course you can always find it by doing this one. Okay, so in any case, if it takes 2 pi over 24 hours, you recover this number. Okay, but if you remember about 7.3 10 to the minus 5 second to the minus, it's a good. Okay, G.
9.8.
What? Okay, always remember to put the, I can also say one, the unit of measure. Okay, now let's look our two friends, ocean and atmosphere. So for the ocean, we can take from the table above. So from the ocean, we can take a typical density, which is 1028 kilogram per cubic meter. We can take a typical variation of density, which is about, let's say, 2 kilogram per cubic meter. And finally, we can take a typical H, which is 1000 meters. Okay, so this is the background density for the seawater. Okay, this is the typical variation that you can find. Of course, it will be 5, it will be 3, it will be 1, but let's say this is we are taking about scale of motion.
Seawater atmosphere.
And this is the typical depth of currents. Okay? Let's look to the atmosphere. So the typical density is 1.2. So we have 3 order of magnitude of different in density. The typical variation of density is 0.03. So this is like 3% with respect to this. This is like 0.2% with respect to this. Okay? So in practice, density in atmosphere varies much more than in the ocean. And finally, we can have a typical height of 5,000 meters. Okay? So these are very general numbers, and we can use these numbers to calculate the value of L and then of U. So for the atmosphere, this is an exercise that you can do it by your note as a homework. So this will be, for the atmosphere, about 500 kilometers with a velocity which is 30 meters per second. For the ocean, we will have 60 kilometers and a velocity which is 4 meters per second. So we have roughly one order of magnitude of difference. It's important to start to think about this order of magnitude. So 500 kilometers, 60 kilometers, 30 meters per second, 4 meters per second. Okay, so ocean has typical length. So what is this length? This is sort of natural length scale, which in our planet gives the opportunity to system, to phenomena, which have rotation and stratification equally important to develop. Okay? So when we look at the table above, we can look for 500 kilometers in the ocean, and we have here hurricane or weather pattern, okay? Because these are the length and the velocity, okay? And of course, we are inside the time scale. We want like 2. If we look at the ocean, we are about 60 kilometers. So here at this, major currents, days to week to season. Okay? So we can roughly say that this is called mesoscale. So it's just the first approach to this word. Mesoscale in the ocean is about 1/10 of kilometers. Mesoscale in the atmosphere is about 100 of kilometers. Okay? So actually this is if it won't be 500, can be like 1,000 kilometers. Okay? But this will be what we are going to study in our in GFD for atmosphere and ocean. So this is another view. Maybe you have already seen this picture, because it's quite common. So if we take again atmosphere and ocean, and we put on the x-axis the time scale, on the y-axis the length scale, and we consider order of magnitude of 10 kilometers, let's say, from here, and 1 day, more or less, here. So we will see that cyclones, planetary waves, something about cloud clusters are the subject of atmosphere GFD. While macroturbulence, boundary layer, cumulus convection, thunderstorm, and so on are not exactly subject of GFD. For the ocean, again, 1 day, 10 kilometers more or less, geostrophic eddies, circulation set, thermaline circulation, fronts. Then we have tides here, which is, let's say, on the border. Then we have internal waves, boundary layers, swell, wind, sea, microturbulence, sun waves, and so on. Okay? So it's important to understand what is the subject of our of GFD. So just to summary, ocean processes are caused by lateral boundaries that do not exist in atmosphere, because of course we have ocean basin, but atmosphere can circulate free over the planet. Atmosphere and ocean are strongly dependent on moisture content that does not exist in the ocean, but in the ocean we have salinity. Okay? Atmosphere is thermodynamically driven. The solar radiation is the main source of energy, while ocean is forced by tides, wind stresses, and surface fluxes. Actually, only tides are due to the fact that there is water. I mean, because wind stress and surface fluxes both depends on the atmosphere. Okay? So the primary source of energy is always the sun. Sun put in circulation the atmosphere. Atmosphere create different pattern of pressure. Different pattern of pressure create a different pattern of winds. And we can move the surface layer of the ocean. Okay? Then we have tides, and then we will see, we will have something related to the thermo-aligned property, so something which is related to temperature and salinity in the ocean, which is another another part of the ocean circulation. Okay, so this is what I wanted to finalize from the last lesson. So now let's start to see how our equations will work, because you already worked with the equation during the course of Riccardo Farnetti. So we said that we are interested to look within the GFD phenomena. So GFD phenomena acts on the Earth is rotating. So we have to transform our the equation, the Navier-Stokes equation, in a reference system which is rotating. Okay. So when we have something like this, so we know that our equation we can just simply write it like here. So the the acceleration is equal to the gradient, pressure gradient, is E plus the body forces and the friction forces. Okay, this is the very general expression for the Navier-Stokes equation. Then we will see more in detail. Okay. Okay. So if we put a system which is rotating, so this is a rotation axis, like the axis of rotation of our planet, okay? And this is a typical trajectory that a point does around this this axis. So we will say capital omega as the rotation rate, and we can say that this is the radius r, which is a vector, and this is, let's say, a certain vector a. Okay, so it's this point. There is a certain origin of the coordinates. This point P is traveling in this direction. Okay, is rotating. So after some time dt, as you remember, we will have this point will have traveled by certain dA. So let's say consider the infinitesimal displacement. So we will have this vector changed by a t to here a t plus dt. Okay, and let's keep this angle, let's call this angle as alpha. So in the case that this vector, or let's say this point whose position is defined by the vector A, is rigidly moving within the rotating frame. So we are just, let's say, fixed on our Earth, and we don't move, so we are just rotating around the axis, the rotation axis. Okay, so we can say that if A is fixed, the variation in time in the rotating frame is 0. Okay? So this means I don't have any kind of velocity because A is a distance. So I'm taking the time derivative of a distance, so I'm calculating the velocity. So A is fixed. There is no velocity related to A. So I want to define the magnitude of this displacement. Okay? So this means that this vector will remain always the same. There won't be any kind of change, nor by angle, nor by length. Okay? So it will change only by the fact that it's rotating. But I can evaluate the displacement, the infinitesimal displacement. So, how much is dA? So, dA is actually the tangential velocity v, which depends, of course, on the rate of rotation rate, multiplied by the time, the infinitesimal time step. But how much is v? V is nothing more than omega r dt. Okay? So this is from your very initial class of physics. Uniform circular motion, tangential velocity is equal to the rotation rate multiplied by the radius. Of course, if I am here, the radius will be shorter, so my velocity will be smaller. Okay? But let's look at, and this is very important, because if you consider our Earth, say like this, okay? So this is the equator, this is the North Pole, and this is the South Pole. So look like this is the axis of rotation is like we are taking a point here or here, okay? P prime. If I'm moving toward the pole, even if I'm fixed, in any case the radius is decreasing. So the velocity, this one, is decreasing. Okay? Okay.
Please, can you kindly take that again? You said the acceleration doesn't change, it's constant.
The acceleration, there is no acceleration, there is no velocity. I'm just taking the only velocity of the system is related to the fact that this point is rotating.
So
This means, sorry?
So is that one now the angular velocity?
Exactly, the angular velocity. Okay, so make a step further. So we can express R as a function of A. So if we consider this triangle here, which will be always the same because it's just keeping its shape without any change. So it's a rectangular triangle which is rotating. So R is nothing more than A by sine alpha. So omega A sine alpha dt. But we know from the vectorial operations that this term here is nothing more than the vectorial product, or vector product, whatever you want to call, between the vector which defines the rotation and the vector A. Okay? So this is how I, which I'm outside, I'm describing the situation. So this means that dA dt, according to me, not I like me, but I as an inertial reference, so I'm outside, I'm somewhere in the space looking at this system rotating. So I'm just saying that since I don't have velocity within the rotating system, the only possibility is this one. So dA over dt will be, and I can even remove this since this is a vector. Okay? So if I want to describe the velocity, the velocity, right? The velocity of this displacement A with respect to the inertial system, this is what I obtain. Simply the vector product between the vector itself and the rotation rate. Okay, so now let's take another vector, we call it B. So B is different from A because such that dB over dt in the rotation framework is different from 0. Okay? So that it does exist a velocity. So it means that if I have a B here, this will start to move, which is the most, let's say, natural thing that we can find. If we have a parcel, it will be part of a current in the atmosphere or in the ocean, and so it will have a velocity. Okay? So this means that if I want to represent again from the inertial frame of reference, I will have now that the only difference between the previous form, the previous definition, is that we have now a velocity in the rotation system. Okay? So it's just a sort of sum between two velocities. So this is the velocity related to the fact, or this, related to the fact that I'm trying to describe a motion from an inertial frame of reference with respect to a rotational frame of reference. Okay? So now we can consider that B, so I can write this. So now we use, instead of B, the velocity. So it's not more displacement like we started at the beginning, but is a real velocity. So we move from something which is meter in something which is meter per second. Okay? So it's still a vector. So if I apply this equation here, I will have that dui over dt in the inertial frame of reference will be, I just substitute B with ui, dui dt in the rotational frame of reference plus the vectorial product between omega and ui. So I just simply substituted B with ui, okay, which is what we are interested in, because ui is this one. Okay? But what is ui? So ui is nothing more than dr over dt in the inertial frame of reference. So the velocity is nothing more than the variation in time of a specific displacement r with respect to time. So if I again use this formula with this, I will have that dr dt ui will be dr dt in r. So I'm just now using this formula by taking not b but r plus vectorial product omega by r. And this is exactly the velocity in the rotational frame of reference, because r is absolute. Okay, so the distance r is, it doesn't have any kind of point of view. I mean, any kind of difference in, doesn't differ in different frame of reference. Okay, so now let's take one step more. So now I can erase this. So now I want to know how much is the acceleration of the inertial velocity, because this is what I have here, but in the rotating frame of reference. So, because this is what I want to know here. I want to know how to transform my inertial velocity, which is the one which is written in the Navier-Stokes equation, in my rotating frame of reference. So I can use this formula and simply substitute this. So I will have dui dtr will be dur dtr plus d dt ur. Okay, I can do it like in one single shot. D dt ur plus. Okay, so I just simply substitute this expression with this expression, and so I have d ur dt r plus, now I have to take the time derivative of this vectorial product. Okay, so it is a product, so I have to do it term by term. When I do the time derivative of omega, omega is a constant, so is it 0? So I just have to take the time derivative of r, so it will be omega by dr dt r. But what is dr dt r? ur. Okay? So the velocity, inertial velocity in r will be ur, the variation of the rotation velocity, the velocity in the rotational time of reference, multiplied by this term here, which is a vectorial product between the rotation rate vector and the velocity r, which is what we want, okay? Because we are measuring ur, okay? Because we are in the rotating system. Okay, last step, which is what we wanted, because it's this one, okay? So this is this part here. So this is equal to di dt dui dt r, which is this one. So is dur dt r plus omega vector product with ur plus, so this is this two term, and then another term which is again omega multiplied by ui, which we know ur plus another vectorial product. So now we are expressing how much is the time derivative of the velocity in the inertial frame of reference with respect to the acceleration or time derivative of velocity in the rotating frame of reference, and we are considering these new terms here. So if I express it, I will have twice this term here plus this term here. Okay? So This is the final form that helps us to transform our Navier-Stokes equation for an inertial frame of reference into the Navier-Stokes equation for a rotating frame of reference. And the difference is that we have to add this term here and this term here. So this is called Coriolis. So this is an acceleration, right? Because we are talking about acceleration. And this is, anyone don't remember what is that?
Linear velocity.
Sorry? Say, don't worry.
Linear velocity.
Centrifugal. Yeah. Okay, so this Coriolis acceleration once come from here, from the fact that we had to add this term here to the expression of the velocity in the inertial frame of reference. And the other one comes from the fact that we are going to take its derivative, okay? Because from the beginning, we know, and this is something that we can remember so it's like a sort of differential operator, okay? So if I want to take to transform any kind of vector from from an inertial time of reference to a rotating frame of reference, I always have to take this equation here. So always the time derivative is equal to the same time derivative plus the vectorial product with the ambient rotation rate. Okay? Of course, when omega is equal to 0, we come back to the usual, okay, dt is equal to dt, which is absolute. Okay? So, interestingly, Coriolis acceleration acts only when something is moving. So only when the velocity is different from 0, we have this term here, which is actually an apparent force or acceleration according to what we want to express, but we are talking about acceleration. So it's apparent. So Coriolis is an apparent force. Coriolis or Coriolia, according to what you want to call it. Well, centrifugal acceleration is due to the fact that we have, let's say, mass, which is rotating, and to the simple fact that they are rotating, there is a pull, outward pull, because if you want to know the direction, so let's look about direction. So if this is my vector omega, and this is u, so this will be omega. So omega vector product with u, so we have omega u, okay? So it's inside. If I take this, so again, let's say here, and this is my r. So omega r is here,
Forces of R.
and then I have to do again omega r. So it's like this. Okay? So since this has to be moved on the right hand side of the equation, this is something which goes on that direction, change sign. Okay? So it's an outward pull. So, and this appears the fact that our Earth, like any kind of body which is rotating, has a flattening at the equator. So the radius, of course, this picture here is strongly exaggerated. We have that this radius here is slightly larger than this radius here. So it's not a perfect sphere. Okay? Actually, if we calculate for our planet, we have that the radius at the equator over the radius at the poles is about 1.003. So is 3 parts per thousand. Okay, not so much, of course. And if we want also to represent the ratio between the centrifugal force and the gravity,
Is that 0.003?
yes, 1.003. So this is about 6,378, I think. And this is 6,357, of course, more or less. Kilometer plus or minus. So if we want to have the idea of how much is the ratio between the centrifugal force and the gravity force, so the centrifugal over the gravity. So the centrifugal is nothing more than omega squared by the radius. Okay, is the magnitude of this one. While the gravity, of course, is the capital G, capital M over R squared. Okay, so this is the universal constant of gravitation. This is the mass of the Earth, and this is the radius. And this is about, again, 1 per thousand. Okay, so more or less are the same order. Okay, so it means that if you would like to draw exactly this two vector here, this vector should be 1,000th of this one. Okay, so it's very, very small. Of course, here is very exaggerated. And the local vertical, of course, is not like this, but is a little bit like this. It's very similar, of course, to the gravity.
So, the gravitational force of attraction should exist between two bodies. So in that case,
So the body is any kind of body. So this is just the acceleration. Okay. So I should, of course, put m here and m here. So if I have like any kind of mass here, okay, so I can express this as a simple acceleration. And
And you said they have the same magnitude.
sorry,
You are saying they have their 1%, the ratio is 1%.
1 per thousand. About 10 to the minus. You can do it. I mean, take the numbers and you do it. So at the end, this term here will be put here. Okay? So we don't want to care about it. So it's just part of the body forces that act, which actually this is G, of course. Okay? So we can say that G, we can write it like. Sorry? This one?
Yes.
10 to the minus 3.
Okay, this 1% of
1 per thousand. There are 2 zeros. 1%, 1. Yes, it's not exactly standard, so. So, just to conclude, so what I usually can say is that I have G hat, which is equal to the G plus centrifugal acceleration. Okay? So, since this is, as we have seen, 1,000th of this one, we can easily put everything inside and consider this body force as the general gravitational term in our equations. So, it's important to say, so what means that now here the gravitation, we can, if you like, we can put a hat here, but we won't care about it when it's important that you remember that here this term has the gravitational and the centrifugal term. But the fact is that now we can write this, and so we have this term here. So we have du dt. Now I can leave all the possible indexes, and here is the right hand side. Okay? So this is the new form for our Navier-Stokes equation in the rotation frame of reference. So the first question that we can do is, okay, what happens if we do not have any forces? So now we are safely on our Earth. We know how to describe our equation, our fluid dynamics equation in our rotating planet. And what happens if all this is zero? So it's a very strong approximation. I'm just saying that gravitation is zero. Okay, it's not possible. But let's say that I don't have any kind of pressure force, no surface force, no body forces. Okay? So it's like to consider like a table which is rotating. And I have a system, and then here I want to describe how is the situation here, not from outside. Because if I am from outside, of course, this is zero. I mean, this is like in quiet, okay? But since this is rotating and I am inside, I want to see what happened here. So I can express this. So this is like two-dimensional system. So this is x and this is y. And of course, in this case, the rotation is parallel to the axis, to the z-axis. So I can calculate the vector product. So in this case, the rotation has only a component over z, because there is no component over x or y, so I can use 0, 0, omega. And then I will have, in the, let's say, more general of case, I will have a u and v component over the plane. Okay? So this is how I can calculate the this Coriolis term for my problem. So this is nothing more than the equation which is ruling how this parcel is moving in this rotating system. Don't forget that this is an apparent force, because physics says that when you are moving from an inertial system of reference to a non-inertial system of reference, you have apparent forces. So we can express, so this is very easy because I have like, so this is, the first term is 0 by omega v. The second is omega u, and the last one is 0. So I will have du dt minus 2 omega v equal to 0, and dv dt plus 2 omega u equal to 0. So if I solve this, I will have u, which is equal to a capital V sine ft plus phi, v, which will be cosine ft plus phi, where f is 2 over twice omega, which is related to this one. V, capital V is the, let's say, capital V and phi are nothing more than integration constant. So when I solve these two equations, differential equation, of course, I will have to take the integral, and then I will have some integration constant. Okay, so I have two equations, so I have two constant of integration. One is v, and one is phi. So v is the initial velocity, because if I do u squared plus v squared by root, I will obtain capital V. Okay? And phi is nothing more than the phase. Okay? So these two are just constant. Depends only how the system has initiated at the beginning. But from here, I can make one step further and calculate x and y, because I know that x dot and y dot, which is dx dt and dy dt, this is the equation which relates the displacement x to the velocity u and the displacement y to the velocity v, so the two components. And again, if I solve this, which means again to solve, to apply the integration to this, to the two components of velocity, I will have x equal to x0, again another integral constant, which comes from the fact that I'm having integration minus capital V over f cosine, again, ft plus phi, and y, which is epsilon 0 plus vf sine ft plus phi. Okay. So you can, of course, take your time and do all this math by yourself. But this is what we want to know. So the position of x and y is equal to an initial position, x0 and y0, plus a term which is changing in time according to a cosine and a sine. So if I'm here, so this will be, let's do it like this, which is better. So let's look to my rotating table from above. So this is x0, this is y0. So this is my initial point, okay, at the at t equal to 0. So what happened after some time? So in particular,
Sir, if the initial position is at a certain height y naught, that means we are going to consider gravity.
no, this is now from the top. There is no gravity. So this is, so z is in this direction. So I'm not consider gravity for the moment. Is let's say that this is, it's, well, it's easier, let's say, in this example. So one thing that we can still know from this one, if we take x minus x0 squared plus y minus y0 squared. So if we do this, so we'll have this in this part, this in this part, v squared by f squared. And so we have v squared over f squared. Okay? So what kind of of path is that one?
Circular with the center external endpoint.
So, and no more, one thing more. So f is equal to 2 omega. So it means that the period of rotation will be 2 pi over f, which is 2 pi over 2 omega, which is pi over omega. While the period of rotation of my system is 2 pi over omega. So it means that the period of this circular motion is is TR over half, over 2. Okay? So, in the time that all the table has done one whole rotation, my parcel here will have done 2. Okay? Because the period is half. And this is the radius. So the radius is given by the initial velocity v, capital V, divided by the frequency f. So when I am at t equal to 0, I have that x will be x0, then this is 0, so this will be according, let's take phi equal to 0. Okay, so the phase, it's an integral constant, so we are quite free to take the value. So if phi is equal to 0, at t equal to 0, this is 0, so we will have x0 minus vf. And y will be simply y0. Okay? So, while at the beginning t is equal 0, so this is 0, cosine of 0 is 1, so this is x0 minus vf. Sine of 0 is 0, so it will be y0. So it means x equal to x0 minus vf, so let's say that this is v over f, and epsilon 0. So this is my position at t equals 0. Now we move to time equal to pi over 2f. So pi over 2f, so it means that if one period is 2 pi over f, if I divide by 4, T4 will be pi over 2f. Right? So after 1/4 of rotation, x will be again x0, and if I want to go here and I want to transform this form, this expression is ft when t is equal to pi over 2f, I will have pi half. Okay? So pi half means 90 degrees. Cosine at 90 degrees is 0, so this term is 0. But y will be, this is 90, this is 1, plus, so y0 plus v over f. So x0 and, so this is t equal to 0, this is t equal, let's say, t4. So the system has rotated in this direction. But if you remember, our system, our ambient rotation is opposite. Okay? So I'm rotating inside a system, and without the fact that I don't have any kind of forces acting on me, the only force is the Coriolis force. What I obtain is that if I continue, of course, I will do something like this. So I will create an oscillation or circular motion, which will have as a period half of the period of the rotation, and as a frequency, of course, twice the frequency of rotation. Okay? So, if we don't take any kind of, so if we stop the rotation, of course, omega is equal to 0, f is equal to 0, and the radius, how much is?
Infinite.
Infinite. It's correct. I mean, this is what happens if I don't have any kind of motion. Okay, so I'm just moving without velocity, without nothing. This is without acceleration, sorry. Because when omega is 0, this is 0, and I have no acceleration, so only constant velocity. So, this is a little bit awkward to have. So, just to have an idea of how the Coriolis Effect acts on the motions.
Luca e Marco usano i toro per investire nei mercati finanziari. Luca studia opportunità.
Okay, this is a short video from National Geographic. It's nice, quite nice to explain.
With a simple game of catch, I think I've found a way to show an effect that will have you doubting your very own eyes.
Because it's not very
But our budding ball players
direct,
on a
no?
specially
It's something that we are not
merry-go-round
experienced.
Are about to demonstrate a rather astonishing optical illusion. Right, here's the game, right? You're going to throw the ball straight to, what's your name, Victor, right? But this time, I'm going to complicate things slightly. I'm going to rotate the merry-go-round counterclockwise. So you throw it whilst it's moving. What's going to happen?
I don't know why, but I feel like if we're going fast enough,
Yeah.
like I might actually be the one catching
They
the ball.
didn't start.
Okay, so you're going to throw it and you're going to catch it. All right.
Yeah, I don't know.
What's going to happen? It's going to veer off to the left. So the ball is going to swerve off to the left. Yep. And you might catch it, possibly. Okay, good. Right, so what's going to happen?
I think it's just going to come straight to me and I'm going to catch it like the champion that I am.
Show me the catch. Okay, great. Right, okay, is that everyone? No, hang on, one more. Spencer.
He's not arrogant.
Just quietly
He's not
confident.
catching it. He's
Really?
not catching it, no.
So what's going to happen to the ball?
I'm catching it. It's right here.
Great, so we've got one saying to go off to you, one saying comes to you, Spencer, and you think it goes straight ahead, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across the spinning merry-go-round, but where will it end up? Will it be caught by the thrower? Will it be caught by the person opposite? Will it be caught by the person to the thrower's left? Or by the person to the thrower's right?
So, what do you think? According to what we did, this is exactly what we are saying now. So this is rotating counterclockwise. Yeah. So is exactly. So
Light.
so which is the correct?
Light. Well, we can
Sorry. So it's exactly the same problem. So we are we are moving something, and what we say here is that the Coriolis force is going to give the effect of Coriolis force is going to give the direction which is opposite to the the rotation, which is in this direction. Okay. So if I'm having a force, because of course there is a force. In our case there is no force, but here there is one force which is throwing, like in the sketch before. So from this point I'm going to throw. And here, since I'm having a velocity which is not equal to 0, I'm having the effect of Coriolis. So what will be? The ball will be caught by the thrower. The ball will be caught by the opposite, on the left or on the right. You say? Right. Right? Everyone?
The rotation is counterclockwise.
Yeah.
So we come by right. Just counterclockwise to that, right?
Any other? All for right?
Go
I'll go for left.
You go for left.
Yes, I'll go for left.
Okay.
I'll go for
Okay. If you win, you will pay to everyone. But if you don't win, okay, you will have a coffee from the other.
Right, in your own time, throw the ball.
Right.
So the answer was D. It was caught by the person on the thrower's right. But camera angles seem to show the ball bent in the air. So is that a camera effect, or are we seeing what they saw? Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to Victor to show us his amazing catching skills, right?
Of course, if it is straight, if it's fixed,
So let me get
goes
this straight. So you threw
right ahead,
the
no?
ball,
Straight.
left your hands, and then what?
And then it just got sucked over to him.
In the air.
Yeah. Perfect throw.
What did you see?
Yeah, curved right in.
Right, so we all agree here the ball curved in midair.
Yeah.
And you didn't cheat this at all?
No, I didn't.
Okay. And do you know why it did that?
No.
No idea. It's called the Coriolis Effect. And it's very simple. It's objects in motion appearing to be, it's an optical illusion, appearing to be deflected off their intended course. So what's actually happening here is you are throwing this ball, you can only throw a ball in a straight line. Can I clear that up straight away?
Yes.
Even though it appears in your eyes to be bending. So you throw the ball straight, it's still going straight, but the table is moving below you. And all of a sudden, look who's in front of that straight moving ball.
So the real trajectory
to the
still
right,
is
because
straight.
you're still looking at the guy you were intending to throw to, and that, ladies and gentlemen, is a Coriolis effect.
Okay. So you can find really many.
Okay, so we know the Earth is spinning.
Well, we can also have a look at this one. This is also nice. It's from the office.
We call this Coriolis. Now you may have heard of the Coriolis effect. Or
This is also nice. You can do it by yourself.
It's not a real force. It's what we call an apparent force. It all depends on your point of view, whether you're looking down from above or, like most of us are, on the Earth, looking from below upwards. Now this is quite a complicated sounding business, but I've got a simple experiment to show it here. Chopping board, we've got a disc of paper pinned to that chopping board, a ruler and a pen. I'm also going to need a little bit of assistance, so Helen is joining me and she's going to spin the disc of paper as if it was the Earth, as if we were looking down from
It doesn't look very
above
nice.
the North Pole. That means we need to rotate that disc anti-clockwise. I'm going to draw a straight line along the ruler
exactly the same. You
as
can
Helen
do it.
rotates that. Just look at what happens. The spin of the Earth means that that straight line is not straight. If you were looking from here, you'd see that the wind would be bending round to the right. That is Coriolis in action in the northern hemisphere. If it was the southern hemisphere, we were looking from below the South Pole, we would spin the disc the other way, clockwise. Try that at home, and you will see that the winds bend the other way, to the left. Now you may have heard that Coriolis makes the water spin down plug holes in different directions in different hemispheres. That turns out to actually be a bit of a myth. Plug holes are just too small a scale for Coriolis to really have any impact.
Plug holes, too small to feel the Coriolis
pressure
effect.
systems, tropical storms rotate anti-clockwise in the northern hemisphere, but clockwise in the southern hemisphere.
Okay? So you can find really very nice videos on YouTube. There is another one from Met Office which is a little bit longer, and you can have a good idea about that. Okay, so now it's very important because we've finalized the Coriolis effect, and which is very important as it's exactly the effect from the fact that we are having a rotating frame of reference. Okay, so it's, as you have seen, is just let's say the first video talked about optical illusion. Of course, physical is not an optical illusion. We call it apparent forces. Okay, good. So